Welcome and hello. This is a video lesson in HY-8, and in this lesson we're going to be talking about the Aquatic Organism Passage, or AOP feature that's built into the program. All right, so the Aquatic Organism Passage, which I'll sometimes refer to as just AOP, determines if aquatic organisms such as fish, turtles, salamanders, and other water creatures are able to pass through the culvert from the outlet end to the inlet end. So right here is my culvert that I have designed and ready for AOP analysis. You can open up the AOP analysis by just going up to the main culvert data dialog box and then clicking on the AOP button right down here at the bottom. That will launch the Aquatic Organism Culvert Crossing Passage Using Stream Simulation dialog box. You can also open up this dialog box by clicking on the button on the toolbar, which is this one right here. You can see the title. It says Run AOP, Stream Simulation. If I click that, I get the same dialog box right here. Now, unfortunately, this dialog box will not resize. I can't make it any skinnier than it is right here. So we're just going to have to work with that. And I should also mention that in the user's manual, we're on chapter 7 now. This is page 123, Aquatic Organisms Passage. So we're going to go ahead and work through the text using the user's manual, which includes this flowchart, which is on page 124. So we'll be referencing this a couple times in the video as well. All right, last part for the introduction is to mention the HEC26 document, which is, let's just go there, go up to the help menu, and then HEC26 is a hydraulic engineering circular document 26 for culvert design for aquatic organism passage. If you click on that, it'll open up a PDF file. Boom, here it is, just like it says. And this is 234 pages of information that deals with aquatic organism passage through a culvert. So lots of background information there. We're not going to be looking at too many details. I'm really just going to be giving you an overview on how this AOP feature works in HY-8. Okay, so without further ado, I'm going to click on the Run AOP button to bring up the dialog box. Over on the left panel, we have our four different pages, which read Input Reach Data, Gradation, Align and Size Culvert, and then finally the results. So if you click on one, that'll advance you to the next page, but it looks like I'm getting blocked by a validation error. So we're going to go ahead and just start right here where we're at on Input Reach Data page. Also along the bottom of this dialog box, we have buttons. So there's a help button, and then there's navigation buttons to the other pages, some of which we've talked about in the lessons, such as the main data input, analyze crossing, energy dissipation, and load flow. Also, between making changes, if you click the Save to File button, that will just save the HY-8 file. And then finally, clicking Back and Next will advance you between these different pages within the AOP interface. Okay, and then the Close button will close this feature. A few reasons why the aquatic organism passage would not be feasible is if the water depth in the culvert is too low, if the water velocity in the culvert is too high, or if there's a step in the culvert where the fish cannot jump up over the step, or if there is excessive turbulence. So this feature here built into HY-8 is to prevent all of those situations where there cannot be aquatic organism passage from downstream to the upstream. All right, so first what we need to do is create our culvert, our crossing and our culvert, and have no errors, which already is the case. We've already done that. And then after that, we'll start with inputting our reach data. What you'll see in these pages is a reference to the step. So step 1, step 2. On the other pages, there's other step numbers. Those steps are referring to the flowchart right here. So step 1, we'll just start here. Design flows for peak, low, and high. So we need to input those design flows. Remember, this is the design flow for the aquatic organism passage. It's not necessarily the peak flow for your 100-year storm. So keep that in mind. But what we have from this dropdown is the list of flows that we already inputted in our flow data right here, our discharge data. So you can use the values that you provided here. So for instance, 0 up to 1,000. If I click on AOP, those are the values in this dropdown, which it looks like 1 CFS is the minimum as well. What I'm going to do for my low flow, I'll just say that's 100 CFS. For high flow, I'll say it's 300 CFS. And then for peak flow, I'll say is 600 CFS. Okay, so we'll see what happens with that later. Step 2 is cross-section data. So now we're going to specify the number of cross-sections upstream of the culvert, and then the number of cross sections downstream of the culvert. The number here is a minimum of 3, but you can type in a larger number. And if I do, say 5, and tab off, it's going to add a total of 5 cross sections upstream of the culvert for me to define that data right down here. So I could add, say, 5 cross sections downstream. That gives me 5 rows and more work to do. So I'm going to keep it simple. Just go with 3 upstream and 3 downstream. And now I get to fill out my cross section data down here. Now I'm going to go back to, first of all, save to file, and then back to the input data. Currently, my culvert stationing starts at 0. This is the upstream end of the culvert. But now that I'm going to have stationing associated with cross sections upstream of the culvert, I'm going to change this inlet stationing to just be 1000. And then that means the downstream station 78. Let's go ahead and just make it 100 feet long. So I'll say it is 1100. Okay, there we go. And then I'll say the drop is 1%, so that would make that 89. Okay, so just updating a few values here. Our slope is 1%. We're dropping 1 foot with a 100-foot run. And now that my inlet station is 1000, I can use positive station values. When I click on AOP, and then this station value here, here, and here would all be less than 1000 because it's upstream. And the way HY-8 does its stationing for culverts is that the stationing number increases as you advance further downstream, a little bit different than some programs. All right, so for what I'm going to do for my stationing is say we're going to have a cross section defined 200 feet upstream of the culvert. The next one will be 100 feet upstream of the culvert. And then the last one will be just 10 feet upstream of the culvert. The stationing for downstream, I'm going to do a similar pattern here. So add just 10 feet to 1100, that would be 1110. And then 100 feet downstream of the culvert would be 1200. And then 200 feet downstream of the culvert would be at station 1300. All right. Don't worry about the calculated slopes right now. That will all be calculated correctly once we add our cross-section data. Also, I should probably mention that the names for these cross sections can be defined. So I could actually just say XS, or how about STA 800? Okay, that's good. I'll go down to the next one. I'll call that STA 900, then STA 1300. Okay, so I renamed those 6 cross sections. Let's start with defining cross section station 800. I'm going to click on define. Enter the number of cross section points. I'll say 6. That gives me 6 rows in the table down here. And then what I've prepared beforehand is my different data. So I'm just going to copy the data I have prepared. This is going to have an invert of 94. So that's higher than the culvert invert. And then right click, or I'm sorry, let me highlight the fields and Control V to paste. Okay, cool. So that's there. We can look at the plot. There is our upstream channel. Dimensions, that's 200 feet upstream of the culvert. All right, so I'll go ahead and click OK. It's updated the Thalweg elevation. I guess that's the same as invert. I need to repeat that process for each of these cross sections. So I'll just do the second one on camera. Again, this is for River Station 900, and say there are 6 cross sections. Okay, then I'm going to paste in the data here. So let me just highlight and paste. It dropped 1 foot over 100 feet. So I'm sticking with that 1% slope, which has been calculated right here. So that looks good. I'm going to do the others now. Yeah, I finished off the others. They all have a 1% slope. Hold on a second. Oh, that's because I need embedment. Okay, hold on a second. They all have a 1% slope. I'm going to say that the downstream slope is, the last cross section is also 0.01, and then save to file. Okay, this slope is off, and that's because I need to change something. I'm going to go back to my input data. Okay, the whole thing closed. Okay, nothing saved. I got to do that again, I guess. Okay, I've got that updated. I put in the stations. I got the cross sections done. There's this one slope that I need to adjust, and I'm going to do that by adding an embedment, I believe. So I'm going to click on Edit Input Data, and then I'm going to have an embedment depth of 24 inches. That's 2 feet. So if I go back to my AOP button, okay, cool. So that worked out. I meant to have that in there earlier. All right, so we're done here. I'm going to click Save to File. Good, nothing crashed. I'm going to advance to the next page now. That's gradation data. Okay, so that's another thing to mention is this validation will pop up. Let's see what we have here. Cross sections. Enter all input data or check data for downstream cross section number 3. Okay, so number 3 downstream is a problem. Something about this one. Oh, I need to enter this slope one more time. There we go. So 0.01, and then save to file. And now let me try to click on gradations. Okay, so let's try that once again, 0.01. I don't think I'm doing anything wrong here. Maybe I have to click off. Okay, I've opened up a new instance, a backup file. We're going to just continue on here. I should be able to click on gradation data. Okay, here we go. So I have all this data filled out already, and this wasn't my original plan, but the other file was just crashing out nonstop, as you noticed. So I'm just going to go ahead and roll with this. The gradation is now step 2 in the flowchart. So let's bring up the flowchart. We're on to step 2 right here. Determine project reach and representative channel characteristics. What we want to do is type in the number of gradations. So to keep things simple, I'm just going to use 1, but you can type in a 2 right here. So, or 12. How about 2? And then if I hit tab, then it gives me a second gradation down here. Here is the stream bed gradation. That's just the name of it, but you can type whatever name you want right here, and then that would help you identify which gradation you're talking about. I'm going to only use one gradation to be simple, so I'll change this back to a 1, hit tab, and then I'm back to just one gradation. You may have different gradations at different stations. So what I'm doing here is I'm saying this one and only gradation extends for the entire range from all the way upstream of the culvert through the stationing of 1300, which is downstream of our culvert. All right, next what we need to do is define this gradation itself. So click on this define button. This will bring up a dialog box where you get to set the D5 through D95 diameter for that gradation. And keep in mind, this is in inches now. So it's good to see that the specified unit system has been honored. These are the numbers I typed in. Actually, hold on. I want to use some different numbers. I want slightly larger numbers than before. So I'm going to type in some numbers here. All right. So those are the numbers I'm going to be using, but you may have to change your numbers for whatever gradation was sampled and tested from both upstream and downstream. You can click on a plot right here just to get a quick look at what that gradation curve looks like. And let's go ahead and click OK. All right, so down below, defining the gradation. Next, what we need to do is identify the Manning's N method for reach cross-section. And then our different options here are Lemurinos, Jarrett, Blodgett, and Musseter. I'm going to go with Blodgett. And then once you make that selection, then the table below determines whether or not that the criteria is met. So what it's calculating is a Manning's N value. And I kind of wish that it extended out to at least 3 decimal places, but all we're seeing here is 0.03, 0.02. This is for the 3 different cross sections, both upstream and downstream of the culvert, and it's for the 3 different flows, which is low flow, high flow, and peak flow. These calculations can be found in the HEC26 PDF document on page 107. Then close that. Let's go up to HEC26. My notes tell me page 107 is where it's at. Yeah, so Appendix C, Manning's roughness. There's a number of different ways that N value is calculated. Here's the first method right here, Lemurinos, if I'm saying that right. And then the next method is Jarrett. So here's N equals this value. Blodgett is next. That's right here. And then a couple other methods. And we're back to the gradation page. What we're told is that the criteria is met 18 out of 18 times, so that's good. If it's not met, then that may mean that your flows are too high. It may mean that your gradation is too small. It could mean a lot of things. Perhaps the actual method that Manning's N is being calculated is not working for you. So yeah, for instance, I changed it to Jarrett right here, and based on the Jarrett N equation, the N values are a lot larger, which is apparently not passing. Criteria is not met. It's a 0 out of 18. So I'm going to use, go back to Blodgett. That worked for me. Okay, so further down, we have reach stability and then culvert bed gradations. That's steps 3 and 4 and also 5. For reach stability, if the stream bed is dynamic and you click yes, then you're good to go. But if it's not, and you also say that the channel stability support design is also a no right here, then your design has been rejected. AOP design cannot continue until the reach has been stabilized. However, if you say yes right here, you can continue on. So this right here is referring to a section in that flowchart, which is right here. Number 3 is the stream bed dynamic equilibrium. And then it asks you that question. So eventually it has to be yes, it has to be in dynamic equilibrium. Next is step 5, that's the culvert bed gradation. Just like upstream and downstream cross sections, we're calculating the material beneath the culvert now, and then we can select the method as before. So go ahead and select your method. That red warning just basically enforced the user to purposefully make a deliberate decision on their Manning's and method calculation. Okay, so everything looks good there. I'm going to save to file and then click on our next page here, which is Align and Size Culvert. This dialog allows the user to make changes to the layout and size of the culvert and immediately see the results in the aquatic organisms passage data. So what you're seeing on the left half right here, this is the culvert data and site data, which we've already entered. If we click on Edit Input Data, that's these two data boxes on the right half of this dialog box. So let me go back to click AOP, move that over, click on Align and Size Culvert, okay? And then over on the right here, this is our results and the different checks that it makes. So the first check, for instance, is the embedment depth. That's step 5. The message it's telling us is the embedment depth is not acceptable. So currently the embedment depth is 0 feet. It's 0 inches. And it looks like the minimum is 2 feet. So we want to change this number here to 24 inches, just like that. Or another way to do it is to leave that at 0 and click this adjust button. And what that's going to do is not only adjust the embedment depth over here, but also adjust the elevation of the culvert. So right now it's 90 down to 89. But if I click adjust, I suspect we're going to have 24 inches here, and this will be 88 down to 87. So I'll click the adjust button finally. And okay, never mind, that didn't happen. We do have 24 inches added here, but then the inlet elevation is 90 and 89. Let me go ahead and check my inlet reach data. Yeah, I wanted that to be 90 and 89. See, I'm looking at the Thalweg elevation. I don't want a negative slope happening. So let's go ahead and just make that update manually. All right, I got that resolved. So now what we're looking at here, I'm back on the input reach data. The Thalweg now goes from 94, 93, 92, and then the invert is 92 to 91, and then 90 down to 89. But we do have 24 inches of embedment. So if I click on Align and Size Culvert, we have 24 inches here. The actual invert elevation now, oops, I meant to change this. This is supposed to be 88, and this right here is supposed to be 87. All right, so if I tab off there, some of the equations have been updated over on the right side. So some of the errors became non-errors, and then we have new errors that appeared apparently. The acceptable embedment depth is 2 feet, and then that is what the embedment depth is. So we're all set there. I'm going to click Save to File. It looks like now there's an error that says the culvert embedment and tailwater invert do not match. So I'm going to have to figure that one out. And then after that, we have a few other checks, such as the culvert bed stability under high flow, the culvert bed stability under peak flow, the culvert velocity, culvert depths, and that's steps 8, 10, and 11 in that flow chart. So let's go ahead and modify our HW divided by D. I think this number is too large. So what we could do is a number of things. What I'm going to first try to do is decrease the flow rates. So I'm going to go back to the input reach data. This is all the way back to step 1. Instead of 5 to 40 CFS, I'm going to click on specify. And then for the value of minimum, and then for the minimum value, I'm going to hit 2. And then for I'm going to specify the maximum as well. Let's call that 5. And then also the peak flow, we'll call that 10. All right, now I'm going to go and save to file and then back to the align and size culvert. Looks like there's still a problem there. I'm not sure how to fix that one. I'll have to do so off camera, but it looks like all the other checks were successful. So yeah, I'd modify what you can. Sometimes that's the invert. Sometimes it's the gradation data. And then sometimes it is the flow rate, the range of flows that will be acceptable for the aquatic organism passage. But anyway, once you have all of your checks successful, and I'm sorry I don't have this one completely passed yet, I'll figure out that later. Go ahead and click on the results table over here to the left. And just like it says, it'll show you the results, which will be the normal depth, velocity, and shear stress. This first table here involves the high flow condition. So that's for cross sections upstream of the culvert, downstream of the culvert, and then within the culvert bed stability itself. That's high flow. And then further down, we have the peak flow analysis, basically looking at the same thing. The upstream cross sections with the normal depth, velocity, and shear, the downstream cross sections with those same parameters, and then the culvert stability numbers at the bottom. All right, well, that was it for this lesson. What we talked about was the aquatic organism passage feature built into HY-8.